Okay, we returned another interesting integral sent to me by Sid. This is problem number 5. We have the integral from -1 to 1 of x squared minus x times square root 1 minus x squared over 253 dx. Okay, to get started with this, what I'd like to do, considering that we've got bounds symmetric around 0 here, right, going from -1 to 1, I want to use the principle of odd and even functions. We have a couple of useful formulas that we can use for if we have an integral going from minus a to a of f of x when f of x is odd, then this is just going to be 0 for the whole integral. And then we have something kind of similar for even functions, but not quite as useful. So if we're going for, let's say our even function is going to be, actually let's make our even function g of x. So for this case, it doesn't tell us anything about what the integral is going to resolve to, but what we can do is update the bounds. We can make the lower bound 0 and bring a 2 out front. But then coming back to our problem, the tricky thing is, so the square terms, these are even just because they have an even exponent, just taken alone. Because if you plug minus x in here, the minus sign gets wiped out by the square. But the trouble is on this x with the 1 exponent, this piece here is actually odd. So what I can do then is actually, let's distribute in this square root here and split this into 2 integrals. So for the first one, we'll just be going same bounds, but then we're going to have x squared times square root 1 minus x squared. And then we'll have this 253. Yeah, let's just leave the 253 for now. And then for the second integral, using this minus x, we'll have a minus between these. And then what's going to happen here, we're going to have x times square root 1 minus x squared all over 253. But then over here, this is going to be an odd function. Just looking at like our definition of an odd function is that if we evaluate f minus x, where this is going to be f of x, then this is going to result in minus f of x. And you'll see that works here, but if you plug a minus x in here, you have a minus sign coming out, the minus gets wiped out by the square. So this is odd. We can use this principle right here, and what's going to happen is this whole integral is just going to become 0, and we just have to deal with this piece right here. But this first one, this is actually going to be an even function, like this right here. Our definition for an even function, if we have g of minus x, it's just going to give back g of x, and you'll notice because we have the everything with an x is squared, and if we plug in a minus x, it's going to wipe out the minus sign. So using this formula over here and rewriting this, what's going to happen is we're going to have 0 for the lower bound, 1 for the upper bound. We'll need to take the 2 up front, but I'm also going to pull out this 253, so we'll have 253 in the denominator. And then we'll have all this other stuff, but what I'm going to kind of rewrite it like this, x squared times 1 minus x squared to the 1/2 power. And the reason I do that is because this right here, this is set up for us where we can use the beta function. Okay, now for the beta function, there's actually many different versions of this formula, but we want to use this one here just because we have this exponent inside the parentheses. So that's going to be this n value right here. And that's also why I split this out, is because the way this is set up, we've got the n also out front of the integral. So we just kind of pull that out right there. So we have our n here. And then all we need to do is use these two exponents, this and use it with this in order to find our z1 and z2 value, and then we can go to our solution in terms of the gamma function. So starting first with this exponent here, we're saying n z1, but n we already know is 2. We already determined that, so we're going to have 2 z1 minus 1 equals this exponent of 2. Add up 1 on both sides. This becomes a 3. Divide by 2, and we have our z1 value. That's just going to be 3 over 2. And then doing the same kind of thing over here for our z2 value. If z2 minus 1 equals 1/2, then z2 must be 3/2. So let's just take this value and plug it into our solution and finish it off. Okay, so first what I'll do is I'll bring down this 1 over 253 in front of the whole thing. And then we'll go to the formula. So this is going to be gamma of z1, which is 3/2. Then our second value, gamma of z2, is going to be also 3/2. And then in the denominator, we just need to add these two values together, 3/2 plus 3/2, that's just going to be gamma of 3. And then in order to reduce this and get this into some kind of numeric value, we have a few formulas we can use. Now, if you use something like gamma of n, this can be expressed in terms of the factorial as just n minus 1 factorial. So here, for gamma of 3, using this is just going to be the same thing as 2 factorial. Get rid of that. 2 factorial, that's just the same thing as 2. And now gamma of 3/2, there's a few things we can do here. First, what I like to do is, it's nice to have one known value for like gamma, and I like to remember gamma of 1/2. This value is just the same thing as square root of pi. So this is nice, but it's not quite what we have here, but we have another formula we can use. If we have something like gamma, let's say n plus 1, we can write this as n times gamma of n. So using that for gamma of 3/2, we can write that as 1/2 times gamma of 1/2. But then just plugging in the value we know, this is going to be the same thing as square root of pi over 2. So then coming back here, we can just kind of plug everything and see if we can simplify it. Now first, in the denominator, 2 times 253, we'll write that as 506. And then for each of these values, gamma of 3/2, we have our value right here. This is going to be square root of pi over 2 times square root pi over 2. But now just cleaning this up, 2 times 2 is 4 times 506 gives me 2024 in the denominator. Square root of pi times square root of pi just gives me pi. So for my final solution to this, we just have pi over 2024. Okay, there you have it. Another good integral sent to me by Sid. Thanks everyone for watching. Have a good day.